Hey everyone, and welcome. Today we're tackling a pretty challenging problem. Find sum of array product of magical sequences. It sounds a bit mysterious, but don't worry. We're going to break it down piece by piece. It's a great problem that combines combinatorics, products, and a really interesting binary condition. So here's the official problem statement. We're given three things: an integer m, which is the length of a sequence we need to form, another integer k, which is a target number of set bits, and an array of numbers called nums. Our goal is to find the sum of array products for all valid magical sequences. Let's first figure out what a magical sequence actually is. Okay, so a magical sequence is basically a list containing m items. Each of these items is an index that we can use to look up a number in the nums array. For example, if m is 3, a sequence might be 0, 5, 2. The magic, as you might guess, comes from that third point, a special condition involving binary numbers. This is the heart of the problem. For any sequence of indices we create, we calculate a special number. We take 2 raised to the power of the first index, add it to 2 raised to the power of the second index, and so on for all m indices. After we get that final sum, we look at its binary representation. If the number of ones in that binary string is exactly equal to k, then our original sequence of indices is magical. Now, this seems pretty straightforward if all the indices in our sequence are unique. For example, if we pick indices 1, 3, and 5, we're basically just setting the first, third, and fifth bits to 1. Simple, 3 set bits. But what happens if we pick the same index more than once? Let's say we pick 1, 1, and 2. We get 2 to the power of 1, plus another 2 to the power of 1, which is just 2 times 2 to the power of 1. That simplifies to 2 squared. This is exactly like a carry in binary addition. The two ones at bit position 1 combine, carry over, and become a single one at bit position 2. This carry effect is what makes the problem really difficult. Let's try to make this concrete with an example. Suppose m is 2, k is 2, and nums has 5 elements. We need to create sequences of length 2. And we need the binary sum to have exactly 2 set bits. The only way for the sum of 2 powers of 2 to have 2 set bits is if the powers are different. For example, 2 to the power of 1 plus 2 to the power of 3. If the powers were the same, like 2 squared plus 2 squared, they would carry over and result in only one set bit. This means for this specific example, a sequence is magical if and only if it consists of 2 different indices. So we need to consider every possible pair of distinct indices. For instance, the sequence 0, 1 is magical. Its array product is nums, 0 times nums, which is 5 times 4, or 20. The sequence 0, 2 is also magical, with a product of 5 times 3, or 15. We have to do this for every single pair, calculate all the products, and then add them all up. A brute force approach would be way too slow for the actual constraints. Just a quick heads up, we'll be walking through the solution using Python, but don't worry if that's not your main language. I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. The core logic is the same no matter the language. So if brute force is out, how do we solve this? The answer is dynamic programming. The key idea is to reframe the problem. Instead of trying to build entire sequences at once, let's build our final binary number 1 bit at a time, from right to left. At each step, which corresponds to an index I from our nums array, we'll decide how many times we want to use that index. To make this work, we'll need to keep track of any carryover value from the previous bit, and of course, how many set bits we've created so far. Let's define our DP state. We can use a recursive function, let's call it DFS, with memoization. It'll need 3 arguments. First, I, the current index from nums that we are considering. Second, shia of j, which tells us how many numbers we've already committed to picking from the previous indices. And third, p, which is that crucial carry value. Now here's the clever part. This function won't just return a single number, it's going to return a map, or a dictionary. The keys of this map will be the number of set bits we could have formed so far, and the values will be the corresponding sum of products for that bit count. Alright, here's the full Python implementation. I know it looks like a lot at first glance, with the helper functions for combinations, the memoization, and the recursion. But the core logic we just discussed is right in the middle. Let's zoom in on the most important part, the main loop inside our DFS function. The absolute heart of this entire solution is this for loop. The variable r here represents our decision at step I. It asks, how many times are we going to pick the index I for our sequence? We can choose to not pick it at all, so r is 0. Or we can pick it once, twice, all the way up to the total number of slots we have left to fill, which is m minus j. Inside that loop, for each possible choice of r, we make a recursive call to solve the subproblem for the next index, which is I plus 1. We update the state. We tell the next call that we've now picked a total of j plus r numbers, and, most importantly, we calculate the new carry. The total value at the current bit position is our old carry p, plus the r times we just picked index I. The carry that gets passed to the next bit is this total, integer divided by 2. After that recursive call returns, it gives us a map of solutions for the rest of the array. Now we have to combine those solutions with our current choice, r. First, we figure out if the current bit is a 1 or a 0. That's simply the total value p plus r, modulo 2. We add this to the set bit count q that came back from the subproblem. Then, we calculate the product contribution for this step. That's the number of ways to choose r slots, times nums at I to the power of r. We multiply this by the sum of products from the subproblem, and add the final result into our answer map for the new total set bit count. So how efficient is this DP solution? The time complexity is roughly on the order of n times m squared times k. Here, n is the length of the nums array, m is the sequence length, and k is our target bit count. This comes directly from the parameters of our DP state. I goes up to n, j goes up to m, and the carry p can also go up to about m. The k factor comes from the size of the dictionary we're building at each step. The space complexity is the same, because our memoization table needs to store the result for every one of these states. Alright, as promised, here is the full solution in Java. You can see the structure is very similar. We use a hash map to represent the state for memoization, and another hash map for the return type of our recursive DFS function. Feel free to pause here and take a closer look. Next up, here's the C++ version. We use a std map of a std tuple for memoization, and std map as our return type to store the counts and products, the logic for combinations, modular exponentiation, and the recursive structure remains identical. And finally, here's the solution in JavaScript. Note that we use big-ints to handle potential overflows during the combination and power calculations before taking the modular, which is a good practice in JavaScript for these types of problems. The overall recursive DP pattern is exactly the same. So let's quickly recap. This problem is a perfect example of how a complex counting problem can be tamed using dynamic programming. The main insight was to shift our thinking from building whole sequences to building the final binary number bit by bit. By creating a DP state that carefully tracked our current index, the number of items we've already picked, and that all-important carry value, we could break the problem down into smaller, overlapping subproblems and solve it efficiently. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. This channel doesn't make any money from sponsorships or ads yet, so if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.